Hello children, in our last discussion we have discussed the capacitance of a capacitor in air medium and when filled with dielectrics. So you are well aware about this formula C equal to Q by V, and this is equal to epsilon naught A by D minus T plus T by K, where D is the distance between plate, T is the thickness, and K is dielectric constant. Now in this class we will discuss the combination of capacitors, that is in series and in parallel as per our syllabus, and energy is stored in a capacitor. Then also we will see the energy loss or gain during sharing of the charges one by one. So let us start today's discussion. First, series combination of capacitors. So let it be three capacitors of capacitance C1, C2, C3 are in series with external source V. So the charge in series, charge on each capacitor will be same, while the potential is distributed in inverse proportion. So we can say let charge Q on each capacitor and potential difference across each capacitors are V1, V2, V3 respectively. So V equal to V1 plus V2 plus V3. If we use the formula C equal to, what is the formula? Q equal to CV. So from there we can use V equal to Q by C, V1 equal to Q1 by C1, and so on. Then we will get Q by C is equal to Q by C1 plus Q by C2 plus Q by C3, where C is the net capacitance. If we use a single capacitor in place of these three, whose capacitance is equal to these three, means storing the charge Q. So C is equivalent capacitance, net capacitance. Here Q is common in both sides, so cancelled out. Then we will get 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. Means we can say the reciprocal of the effective capacitance is sum of the reciprocal of individual capacitance. And remember, note down here, effective capacitance in series combination is less than the list of all individual capacitors. If we take two capacitors of 1 farad, 2 farad capacitance connecting the series, then net capacitance will be less than the list here, the 1 farad. Now parallel combination of capacitors. Once again consider three capacitors C1, C2, C3 are connected in parallel with a battery of potential difference V. In parallel, the charge will distributed on each capacitors depending upon their capacitance, while potential will remain same across each. Let the charges on each capacitors Q1, Q2, Q3 are on C1, C2, C3 respectively, and potential difference will be V. So if we can use the conservation of charges, means Q equal to Q1 plus Q2 plus Q3. But we know Q equal to CV. So Q1 equal to C1V1, Q2 equal to C2V, Q3 equal to C3V, and Q equal to CV, where C is the equivalent capacitance. So we can say CV equal to C1V plus C2V plus C3V. V can be cancelled. So C equal to C1 plus C2 plus C3. Now compare it whatever you studied in class 10, that is combination of resistors. If R1, R2, R3 are the three resistors connected in series, then their R equivalent equal to R1 plus R2 plus R3. So capacitors and resistors equivalent are opposite of each other. So C equal to, we can say, if n capacitors, then summation of all. Now the effective capacitance in parallel combination will be greater than the largest of all individual capacitors. Now this part, energy stored in capacitor, is very important area. So try to understand this one. If any query, instantly you should inquire. Let a parallel plate capacitor is connected with a battery V. At any moment, charge is plus minus Q, means over the positive plate plus Q charge and over the negative plate minus Q charge. Now if a small charge, that is dq, is transferred against the potential difference V, here see this plus dq charge is transferred against the potential difference, means we are saying against the field, the direction of electric field will be positive to negative. So here some work will be done, and that work done stored as electrostatic potential energy. So in transferring a small charge plus dq, a small work is done, and that work done, we can say dw equal to v dq, where v is the potential difference across plate. Also we know v equal to q by c, where c is the capacitance, then dw equal to q by c. Now if we consider initially capacitor was having no charge and the total charge transfer is q, then the total work done to transfer charge q is integration 0 to q by c dq, and we can remember integration of x dx, that is x square by 2. So here integration of q dq will be q square by 2 dq, and 1 by c can be taken out. Then we substitute the upper limit and lower limit. Then we will get u equal to q square by 2c. If we substitute the value of q, then we will get u equal to 1 by 2 cv square, because q equal to cv. And also in the form of q or v, we will find u equal to 1 by 2 qv. In this energy store, another important term or quantity is being asked, that is energy density. Energy density is energy store per unit volume. If area of plate is A, distance between plate is D, then volume will be A into D. So U equal to, that is small u, energy density U by AD. Now we can take the value of U, any one of above 3. Here we are taking q square by 2c, and we can put the value q equal to sigma A, where sigma is the surface charge density. Then we will find energy density equal to 1 by 2 sigma square by epsilon naught. Also, from the Gauss law, we are knowing electric field between the plate is. What is, anyone can say? Yes, sigma by epsilon naught. So energy density equal to 1 by 2 epsilon naught E square. Now compare what is the energy stored in series combination and in parallel combination. In series we know 1 by C equal to 1 by C1 plus 1 by C2 and so on, and U equal to Q square by 2C. So in place of 1 by C in this, we can substitute this value. Then what we will get? U equal to Q square by 2 within bracket 1 by C1 plus 1 by C2 and so on. So see, this term will be Q square by 2C1, Q square by 2C2, Q square by 2C3, and it is the energy stored in individual capacitors. So U equal to U1 plus U2 plus so on. Means the total energy stored in the system is the sum of energy stored in the individual capacitors. Now the same way we can find the energy stored in parallel capacitors. We know equivalent capacitance in series is sum of individual capacitance. And now here use U equal to 1 by 2C square. Why we are using? Because here in parallel, potential across each remains same. So only we have to substitute the value of V. Here in series, charge remains same, so we have used this formula. So that U equal to 1 by 2 C1 plus C2 plus C3 and so on V square. Now 1 by 2 C1 V square plus 1 by 2 C2 V square, and this will be the energy stored in individual capacitors. So U equal to U1 plus U2 plus U3 and so on. So see, the energy stored in each combination is the sum of energy stored in individual capacitors. Now another part which is being asked in 2 marks or 3 marks section, that is, what happens to the energy while shearing of the charges. In shearing we can use conservation of charges. Let two capacitors of capacitance C1 and C2 having the charge Q1 and Q2 and potential V1 and V2. So the total charge after shearing must be equal to total charge before shearing. Here we are taking in parallel. So charge after shearing, that will be net capacitance into V, that is C1 plus C2 into V, is equal to, before shearing, first capacitor having the charge Q1, so that is C1 V1 plus C2 V2. From here V equal to C1 V1 plus C2 V2 by C1 plus C2. Now we can find the energy before shearing and after shearing. So before shearing, energy U initial equal to half C1 V1 square plus half C2 V2 square, and the total energy after shearing, it will be sorry 1 by 2 C1 plus C2 V square. Now how we can find whether energy loss or gain? So best option is find the difference between initial and final. Generally we used to find the difference final minus initial. Here or anyone we can do initial minus final. If we are doing the difference initial minus final and that difference is positive, we can say initial energy more, finally less. Let it be here we are doing U initial minus U final, and just subtract these two, we will get this result. C1 V1 within bracket V1 minus V2 square divide by 2 C1 plus C2. And this quantity C, capacitance, is positive quantity, so product of these two positives, summation will be positive, and a square of difference, that will always positive. So we can say U initial minus U final is greater than 0. It means initially energy more, finally means after sharing energy reduced. So there's a loss of energy, and this energy loss will take place in form of heat and electromagnetic radiation. So these are today's discussion. Thank you.